Fourier transforms are a bit like an attractive mathematician, hard to understand but irresistible. So let's recall that fk would equal 1 over root 2 pi with an integral of minus infinity to infinity of fx e to the minus I kx dx, where fx is just this function. So we have this function here where x is greater to 0, and we know when the function is 0, x is less than 0. So let's take fk and let's plug in the function. We're going to have 1 over root 2 pi, but instead of it being minus infinity, we know that fx equals 0 when x is less than 0, so that's going to be 0, and that's going to be infinity. Let's take this and shove it in, x minus 2x, and then let's put this in, e minus I kx dx. We now combine the exponents, so we know through exponential rules that this would then become, oh god, do I have to write out? Oh, okay, I'll do it. 1 over root 2 pi, 0 to infinity, and that's going to be x e to the minus 2 plus I k x, because remember x is in both, so we can pull that out, and then dx, forgot that. So it's now just a standard integral. So the standard integral of 0 to infinity of x e to the minus ax dx would equal 1 over a squared. Now this is something that you need to remember. For the real part of a where it's greater than 0, a in our situation is just 2 plus ik. So the integral of 0 to infinity of x e to the minus 2 plus I kx dx would be 1 over 2 plus I k squared, because that's what a is, so we've just plugged this in here. So now we have fk equals, so remember this, don't forget that, 1 over root 2 pi multiplied by 1 over 2 plus I k all squared. You can rationalize the denominator, however, I think that this is the easiest way to represent it. If you rationalize the denominator, you're going to get something like 4 minus 4ik minus k squared on the top, all divided by 4 plus k squared all squared. That looks more silly, whereas this right here, 1 over root 2, 2 plus ik all squared, is the Fourier transform of this.